In the next example, we're going to reverse our direction a little bit, and we're going to look at a function that's nowhere differentiable. Nowhere differentiable means that f prime of z naught does not exist for any point in the complex number. So there's nowhere where we can make sense of the derivative of this function. And let me just notice here, if we write, again, we write z as x plus iy, which is a helpful thing to write, then this is saying f of z is x plus 4yi, I guess. It doesn't matter where you put the I. All right, so how do you prove that such a thing does not exist? Well, you write down your limit, and then you do two different approach paths, right? And or at least you try to find two different approach paths. And so let's do exactly that. And let me just observe that if we write z as x plus iy, then delta z is meant to represent a small change in z. So what should a small change in z be if x plus iy is? Well, a small change in z should correspond to a small change in x plus I times a small change in y. Right? So in particular, when we're looking at f prime of z naught, which is the limiting value rather of as delta z goes to 0 of f of z plus delta z, f of z naught plus delta z minus f of z naught over delta z. What we're really going to be looking at here for this problem is if we write z naught as x naught plus iy naught, we're going to be looking at the limit as delta x delta y goes to 0, 0, because that's what happens as delta z goes to 0. Both of these guys have to go to 0. F of x naught plus iy naught plus delta x plus I delta y minus f of x naught plus iy naught over delta x plus I delta y. All right, and the reason why we're doing this is just so that, well, first of all, to compute f, we need to invoke x's and y's, but then we can be pretty clear with our approach paths if we figure out what this looks like. Okay, so to that end, let's compute this limit for this particular f. So delta x delta y goes to 0, 0. Let's collect our real parts for the input, because that's what f needs to know about. And then we're going to collect our imaginary parts. That's what f needs to know about. And then we'll compute them all on the same line. So I'm going to leave this last term in the numerator alone, and we're going to leave the denominator alone. All right. So f, if you rewind or look in your book, it's I take my real part, and then I add 4 times the imaginary part, times I. So again, f is going to be take our real part, but then we're going to quadruple the imaginary part. All right. Sorry, this is just a lot of writing. None of the algebra is particularly difficult. It's just a lot of writing. Let's do some mental math here. We have an x naught, we have a minus x naught from that negative sign, so that cancels. We have a 4y naught I, and we have a negative 4y naught I, so those cancel. What we're left with is delta x plus 4 delta yi over delta x plus delta yi. And so now we can see that, for example, if delta y was 0, so we are approaching 0 along the x-axis, we should get delta x over delta x, which is 1. So here's our curve C1, and then here's going to be our curve C2. If we approach along the y-axis, we will probably get something like 4. So let's do exactly that. We're going to approach along C1. And so along C1, delta y is 0 along C1. So we're really just looking at the limit as delta x goes to 0. Delta x plus delta y is 0. Delta x plus delta y is 0. So that's the limit as delta x goes to 0, delta x over delta x. And that's the limit as delta x goes to 0 of 1, which is 1. So along the real axis, it looks like this limit should be 1. And now let's look along the imaginary axis. So we're going to approach along C2 in the picture. So that's where delta x is 0. All right, I'm going to scroll down a little bit. So we're going to look at the limit as delta y goes to 0 now, because delta x is 0 of what? Delta x plus 4 delta yi, delta x is 0, over delta x plus delta yi, where delta x is 0. So that's the limit as delta y goes to 0 of 4 delta yi over delta yi. But that's the limit as delta y goes to 0 of 4, because they cancel. And that's 4. Aha. So if we approach, remember z0 here was arbitrary. And what happened was we approached the limit along two different approach paths. We approached the point rather along two different approach paths and computed the limiting value along those approach paths. And we got different numbers. Since we get different numbers, the limit does not exist. And the limit that we were computing was f prime of z0. And was z0 special? No. z0 was arbitrary. It exists nowhere. And this is very curious because if we were thinking about functions of a real variable, how would you go about computing the derivative of this function? Well, you'd get a 2 by 2 matrix, and it's the matrix of partial derivatives. And what this is saying is somehow being complex differentiable is a stronger notion than just having a real derivative in the sense of multivariable calculus. So what this opens up is it opens up a lot of really cool results that we're going to get to. And somehow there's something very special just about dividing in this definition of derivative by delta z, and the fact that there's some complex arithmetic going on in the background. It forces the functions that we look at to be quite special. This is a very innocent function. This is linear in both entries. This is, if this was a function of a real variable, you could write down the derivative of this in a second. But in C, this doesn't exist. And what we're going to try to do is we're going to try to figure out why this doesn't exist and what kind of tests can we do instead of sort of luckily guessing different approach paths. And that will be the subject of the next section, and we get there soon enough.